Hello everyone! In this video we will continue to examine topic 12.1, the interaction of matter with radiation, and in particular the Bohr model of the atom. So, the Bohr model of the atom is a model of the atom that we've seen before in a number of different forms, and sort of there are different variants that are sometimes introduced, but it's basically the first quantized model of the atom that's introduced. Often it's introduced in chemistry with electron shells, but basically any quantized energy level model stems from the original Bohr model of the atom. And we're going to study it in depth, in part because it is arguably the first major application of the wave function. So the application of psi to a particular problem with tremendously precise predictions, unexpectedly so, and a wildly successful application. Now, in this application, we're going to make a number of assumptions which are a little bit strange. So we're going to sort of mix classical physics and quantum physics, and in our modern understanding of how the atom works, the Bohr model of the atom makes a number of assumptions that are inaccurate or can be refined. But as a step along the way of our understanding and in the actual historical development of quantum mechanics, it's almost unparalleled in importance. So let's dive in a little bit. If electrons are described by the wave function, that is, what it is for an electron to exist is just for a wave function that corresponds to the electron to exist. As it turns out, we can derive the quantized energy levels of the hydrogen atom. And as a result, we can derive the exact frequencies of the emission spectrum of hydrogen. And this is an astounding thing to be able to do. So we had known for years exactly how it worked. We had sort of a model of these quantized energy levels, but the values of the energies themselves, right? Like that this was 13.6 electron volts, and the next one up was around 3, and so on and so forth. That was not known. And this application of the wave function will allow us to, from first principles, derive those values, which is really quite astounding. And the way we do it is we consider the hydrogen atom as a proton surrounded by the wave function corresponding to the electron, where the electron is a two-dimensional, or sort of one-dimensional wrapped around standing wave around the proton itself. So the wave function is modeled as a literal wave, okay, with peaks and valleys. And the wave function is only stable at integer wavelengths around the proton. That's the key assumption here. So sometimes it's easier to see with sort of more peaks here. If you have a standing wave, the wave is going to oscillate between this shape and this one. Okay, so just like a traditional standing wave, it's going to oscillate, sort of wobbles in and out. And the idea is that as the electron orbits, you can think of the wave function in your head as sort of the path of this wave that it's tracing out, and you get a standing wave when exactly an integer number of wavelengths fit around the proton. And the only stable states for the electron to be in are the ones where it is stable in this standing wave formation. Notice that if this is the n equals 3 state, that would correspond ultimately to the third energy level. And there are 3 peaks here. 2 looks like this, kind of like a peanut oscillating back and forth. And 1 is sort of funny. At any given time, you have a peak on one side and a trough on the other, and it just looks like sort of a circle wobbling back and forth. And then higher order peaks will have exactly the number of peaks as the energy level itself. Okay, and so this is our model for what is happening fundamentally. And what we're going to do over the course of the next few videos is we're going to take that model And we're going to derive a number of results. So that model plus sort of some classical physics stemming from the relationship between the proton and the electron will allow us to derive those exact values of the energy levels of the hydrogen atom, the exact values here, which is an astounding, just to repeat, an astounding prediction, and one of the first real pieces of evidence that that quantum mechanics has significant bearing in reality.